Okay, so students, now I will talk about the next experiment, which is optical time domain reflectometer. So here I will introduce you to a new segment, circuit segment, which is called optical circulator, which is attached to this right runner system. And the working principle of a circulator is like this. So it's a 3-port device. The light will come from port 1. It will go through this circulator and then it will reach port 2. And from there the light will get reflected, and the reflected beam will go to port 3. It will not be allowed to go to port 1. So you can call it as input port, this as your intermediate port, and this as your output port. And we'll make use of this element in this experiment, okay? Alright, so here you can see the circulator. So this one is your input port, this one is your intermediate port, and this is your output port, okay? So the light from 1550 nanometer has been connected to the input port of the circulator with the help of a patch cord, and the intermediate port has been connected with the patch cord, okay? And the reflected ray will come back and then it will reach port 3, okay? The port 3 has been connected to the photodetector 3 with the help of this patch cord, okay? And to see the reflected waveform, we have connected it, the respective adjacent port, to the channel 2 of this DSO, which is attached to this light runner system, okay? And in this experiment, what we will do is that we will try to measure the time delay between the incident wave and the reflected wave. But it's very difficult to use the same photodetector for measuring the input and the output waveform, right? So what we will do in this experiment is that we'll try to make use of the clock, which actually controls the frequency of the input wave, and we actually have connected this clock to the channel 1, which is also called a triggering channel, okay? So now we can actually see both the clock signal or the input signal as well as the reflected wave. Now the question is from where the reflected ray will come. So if you can revisit Fresnel's equation, it says that whenever light will see an interface of two different diffractive indices, some part of the light will get reflected, right? Now in this experiment, in this case, through optical fiber the light will be guided. The refractive index of the core is 1.46, 1.45, and as soon as it reaches the output end, it will interact with air. So there will be an index contrast of 1.46 and 1, and as a result there will be some part of light which will get reflected, okay, and will mainly control that part. So here, as a result, what I can say is the patch cord which has been connected to the input port is actually left free. Okay, so it's just tapped. So you can say that at this interface of 1.46 and 1, some part of the light will get reflected, and that reflected ray will go to port 3, and we'll try to measure that. Okay, so if you can see this OTDR segment, here you can, in the top row, it's called pulse. We can fix it to any value of our choice. I have fixed it to 1 microsecond, and the second port will give you the power. I actually kept it as 100%, okay? And then whenever I will click on start, we'll see both the waveform, the incident and the reflected, okay? And if you can see, both the pulses are actually almost superposing with each other, okay? Which it should be, because the reflected ray is coming from a very small segment, okay? More will be the distance, more will be the separation. So here, since the segment is very small, so the separation between the input pulse and the reflected beam is very small, okay? Now whenever I will connect this to the spool that we are having, so we are having 3 spools with 2 ports, so 1 kilometer, 2 kilometer and 3 kilometers. So jointly we can get 6 kilometers as a whole, okay? How will you do that? just like what we did in our dispersion experiment. So we'll connect this patch cord to one of the port of a particular spool. The other port will get connected to the input port or the one port of the second spool, and this way we can get the 6 kilometer long fiber. Okay, and the output from the last fiber spool actually has been left free. So now we can actually see what will be the reflected wave pattern. Okay, I'll just connect this to the one of the input port of the fiber spool and you'll see the magic. Now you can see that there are multiple peaks which actually has come. Now, since the light is actually propagating a distance of 6 kilometer, you should get only one peak, right? Only one peak after this clock pulse. But why are you getting these 2 or 3 peaks? Just give it a thought, okay? Because I already said something which will help you in getting this answer. So here we are actually getting this yellow curve is actually giving us the reflected beam after passing through 6 kilometers, but we are not using a single fiber of 6 kilometer long. We are just connecting 3 spools. Okay, maybe you can give it a thought that why are you getting 3 peaks. And now how will you measure the separation? We need to stop it, and then you need to get the separation of the input pulse with the farthest peak. Okay, because that will give you the largest separation, which in our case is 6 kilometer. So the way we'll do it is the following. We'll click on this measure button. Okay, we need to measure the time base, so we need to click on this, and then from this we can get cyan curves which will tell you that the temporal separation. So one part will be along the circular along the clock frequency or the clock wave, and the other part will be along the furthest peak. So now if we can click on this calculate, we'll get the separation, and from this temporal separation you can actually get the length of the fiber which the incident wave actually travels. So in this experiment I will provide you this snapshot, and using the time-based scale you can actually get the temporal separation, and from that you can predict the fiber length, and then from that result I will compare it with my results. Okay, so I will not tell you the fiber length, you need to evaluate it. Okay, so that's all about this experiment. Thank you.